Hey everyone, Osama here. Welcome back to another deep dive into the fascinating world of technology. Today we're diving deep into the world of system buses. These are the unsung heroes of your computer, the information highways that connect your CPU, RAM, graphics card, and everything else. Imagine your computer as a bustling city. The CPU, RAM, and graphics card are like the city's essential buildings, hospitals, schools, and offices. But what connects all these buildings? Roads and highways. That's exactly what system buses do in your computer. Think of them like the circulatory system of your PC, carrying vital data between components. Just as blood carries oxygen and nutrients to different parts of your body, system buses transport data to where it's needed most. There are three main types of buses: the data bus, the address bus, and the control bus. Each of these plays a crucial role in ensuring your computer runs smoothly. The data bus carries the actual information, like your cat videos and spreadsheets. Whenever you open a file or stream a video, the data bus is hard at work, transferring that information to your screen. The address bus tells the data where to go, like a GPS for your data packets. It ensures that the information reaches the correct destination, whether it's your RAM, CPU, or storage. And the control bus directs the flow of traffic, making sure everything runs smoothly. It's like the traffic lights and signs that regulate the flow of vehicles on the road, preventing data collisions and ensuring efficient communication. But just like our roads need upgrades to handle more traffic, system buses need to evolve to keep up with the ever-increasing demands of modern computing. As software becomes more complex and data-intensive, the need for faster and more efficient buses becomes critical. That's why we've seen a constant evolution of bus architectures, each one faster and more efficient than the last. From the early days of simple parallel buses to the sophisticated serial buses we use today, the journey has been remarkable. So buckle up, because we're about to take a trip down memory lane, exploring the evolution of system buses from the early days of ISA to the lightning-fast PCIe of today. We'll look at how each generation of buses has improved upon the last, making our computers more powerful and efficient. The ISA bus, or Industry Standard Architecture, was one of the first bus architectures used in personal computers. It was revolutionary for its time, allowing multiple devices to communicate with the CPU. However, it had its limitations, especially in terms of speed and bandwidth. Then came the PCI bus, or Peripheral Component Interconnect. This was a significant leap forward, offering higher speeds and more efficient data transfer. It became the standard for many years, supporting a wide range of devices from sound cards to network adapters. Today we have the PCIe or PCI Express, which is the gold standard for high-speed data transfer. It's used in everything from gaming PCs to servers, offering unparalleled speed and efficiency. The PCIe bus has multiple lanes, allowing for simultaneous data transfers, making it incredibly versatile and powerful. As we look to the future, the evolution of system buses will continue to play a crucial role in the advancement of technology. With the rise of AI, machine learning, and big data, the demand for faster and more efficient data transfer will only grow. Who knows what the next generation of buses will bring? So, the next time you use your computer, take a moment to appreciate the unsung heroes working behind the scenes. These system buses are the backbone of your PC, making everything possible. Thanks for joining me on this journey, and stay tuned for more tech deep dives. Our journey begins in the 1980s with the Industry Standard Architecture, or ISA bus. This was a time when personal computers were just starting to become a common sight in homes and offices. The ISA bus was a critical component in this revolution, providing a standardized way for different parts of the computer to communicate with each other. ISA was like the Model T of system buses, simple, reliable, and revolutionary for its time. Just as the Model T made automobiles accessible to the masses, the ISA bus made it possible for a wide range of peripherals to be added to personal computers, greatly expanding their capabilities. It allowed for add-on cards like sound cards and modems, ushering in a new era of PC customization. Users could now enhance their computers with better audio, faster internet connections, and other features that were previously unimaginable. This flexibility was a game changer, making PCs more versatile and powerful. But as technology advanced, ISA started to show its age. The demands of new software and hardware were pushing the limits of what ISA could handle. It became clear that a more advanced system bus was needed to keep up with the rapid pace of innovation. With a maximum bandwidth of just 16 megabytes per second, it was like trying to stream 4K video over dial-up. Something had to change. The limitations of ISA were becoming a bottleneck, preventing computers from reaching their full potential. Enter EISA, the Extended Industry Standard Architecture. This new bus was designed to address the shortcomings of ISA while maintaining compatibility with existing hardware. It was a significant step forward, offering improved performance and greater flexibility. Introduced in 1988, EISA was like giving the Model T a fresh coat of paint and a slightly bigger engine. It retained the simplicity and reliability of ISA, but added new features that made it more suitable for the demands of the late 80s and early 90s. It offered some improvements over ISA, including 32-bit addressing and a modest bandwidth boost to 33 megabytes per second. This was a significant upgrade, allowing for faster data transfer and better performance in a variety of applications. However, ISA was still too slow for the emerging world of high-performance graphics and multimedia. The demands of these new applications were pushing the limits of what ISA could handle, just as they had with ISA before it. The PC world needed a more radical solution. The limitations of both ISA and IISA highlighted the need for a completely new approach to system bus design, one that could keep pace with the rapidly evolving world of computer technology. This realization set the stage for the development of even more advanced bus architectures in the years to come. In 1992, the Peripheral Component Interconnect, or PCI, bus arrived on the scene. PCI was a game changer, offering a quantum leap in performance with a blistering, for the time, 133 megabytes per second bandwidth. But PCI wasn't just about speed. It also introduced the concept of plug and play, making it easier than ever to install and configure hardware. Remember the days of fiddling with jumpers and dip switches? PCI made those nightmares a thing of the past. PCI's reign wouldn't last forever, though. As technology marched on, even its impressive bandwidth started to feel limiting. Section 4. PCIe. Unleashing the power of serial communication. In the early 2000s, a new champion emerged, PCI Express, or PCIe. This was a time when technology was rapidly evolving, and the need for faster, more efficient communication between computer components was becoming increasingly critical. The introduction of PCIe was a game changer, setting new standards for performance and reliability in the world of computing. This revolutionary technology marked a fundamental shift in bus design, moving away from the parallel communication of PCI to a high-speed serial architecture. Unlike its predecessor, PCIe utilized point-to-point connections, which significantly reduced latency and increased data transfer rates. This meant that computers could handle more complex tasks with greater efficiency, paving the way for advancements in various fields such as gaming, data processing, and artificial intelligence. Think of it like this. PCI was like sending a bunch of pigeons with messages strapped to their legs. Each pigeon represented a piece of data, and they all had to arrive at their destination simultaneously for the message to be complete. This method was not only slow, but also prone to errors, as any delay or loss of a pigeon could disrupt the entire communication process. PCIe is like sending a single super-fast carrier pigeon. This pigeon can carry all the data at once, ensuring that it arrives quickly and accurately. The efficiency of this method is unparalleled, allowing for faster and more reliable communication between computer components. And with each generation, that pigeon just gets faster and faster. PCIe has seen multiple iterations, each one improving upon the last. From PCIe 1.0 to the latest versions, the speed and performance have increased exponentially, keeping up with the ever-growing demands of modern technology. PCIe offered a number of key advantages over its predecessors, including multiple lanes, which is like adding more lanes to a highway. This multi-lane approach allows for parallel data transmission, significantly boosting the overall bandwidth, and enabling the system to handle more data simultaneously, which is like adding more lanes to a highway, allowing for multiple data streams to travel simultaneously, significantly increasing bandwidth. This is crucial for applications that require high data throughput, such as video editing, 3D rendering, and large-scale simulations, allowing for multiple data streams to travel simultaneously, significantly increasing bandwidth. Full duplex communication, where data can travel in both directions at the same time, further enhances the efficiency of PCIe. This bidirectional data flow ensures that information can be sent and received simultaneously, reducing wait times and improving overall system performance. Where data can travel in both directions at the same time, unlike the one-way traffic of older buses, this capability is particularly beneficial for tasks that require constant data exchange, such as online gaming, real-time data analysis, and cloud computing. Unlike the one-way traffic of older buses, and backward compatibility, meaning older PCI devices could still work with PCIe systems, ensuring a smooth transition. This backward compatibility is a significant advantage, as it allows users to upgrade their systems without having to replace all their existing hardware. Meaning older PCI devices could still work with PCIe systems, ensuring a smooth transition. This feature has made PCIe a versatile and future-proof solution, capable of adapting to new technologies while maintaining support for legacy systems. As we continue to push the boundaries of what computers can do, PCIe remains at the forefront, driving innovation and enabling the next generation of technological advancements. Section 5. PCIe Everywhere, from graphics to storage. Today, PCIe is the undisputed king of system buses. You'll find it in everything from high-end gaming PCs to enterprise servers. Its high bandwidth and low latency make it ideal for demanding applications like graphics cards, where modern GPUs are power-hungry beasts, and PCIe gives them the bandwidth they need to render stunning visuals. NVMe SSDs, these super-fast storage devices rely on PCIe to achieve their blistering read and write speeds. And networking devices, where 10 gigabit Ethernet and faster network cards leverage PCIe to handle massive amounts of network traffic. PCIe has become the backbone of modern computing, enabling the high-performance devices and applications we rely on every day.